Let's again look at our prototype reaction. Methyl iodide reacting with hydroxide ion to form iodide ion and methanol. This reaction is believed to be a one-step reaction, where the two reactants must collide in order for the reaction to move in the forward direction. Of course, for the reaction to go in the reverse direction, the two products must collide. There are ways of telling this that involve measuring rates starting with different amounts of reactants. We'll leave the mathematics of this for a future chemistry course. The point is that one can envision this reaction happening in one step or in multiple steps. You cannot tell this from the balanced equation. This has to be determined experimentally. We view this as a one-step process. In the one step, the new CO bond forms, the hydrogens flip over, and the old CI bond breaks, all in one step. And same with the reverse process. The old CI bond reforms, the hydrogens flip back over, and the CO bond rebreaks. You could imagine, though, that this could be a multiple step process. For example, what if the ion and the molecule just sat around and waited for the iodine just to come off? Well, in that case, that's step number one. A second distinct step would then be hydroxide coming on and forming the CO bond. Likewise, the reverse process could be multiple steps. Wait for the CO bond to break, and then an iodine comes on and forms a new CI bond. So one can visualize or imagine a one-step or a multiple-step process. So, what determines how fast a reaction goes? In other words, what determines a reaction's rate? A reaction rate essentially tells us how many molecules react per unit time. These factors are generally broken down into two categories: those that affect the frequency of collisions, and those that affect the fraction of successful collisions. One factor that affects the frequency of collisions is the concentration. The more molecules you pack into a given volume, the more collisions there will be every second. Imagine being in a room with two other people, all of you blindfolded. Now start walking around. Every once in a while there will be a collision. Now, be in that same room with 100 people. There will be many more collisions over the same time period. The temperature also affects the frequency of collisions. We know that as the temperature is increased, the molecules move faster. Go back to the room where you're blindfolded, and instead of walking slowly, now run. A lot more collisions. But we have to realize that not every collision successfully leads to products. The collision needs to have enough energy to move the atoms to their new positions and break the bonds that need to be broken. How much energy that is needed is dictated by the activation energy. Temperature comes into play here too, as increasing the temperature leads to a higher energy collision. So more will have the sufficient energy to overcome the activation energy. There is also what is called the orientation factor. The atoms have to be lined up correctly such that the new bonds form in the proper location. We can think about collision energy with our models. If hydroxide comes in with very little energy, it's not going to be able to force those hydrogens over to the left and break the CI bond. It has to come in with sufficient energy to push the hydrogens over and break the CI bond. We can think of the amount of energy required as the activation energy of the process. Likewise for the reverse process, iodine has to come in with sufficient energy to push the hydrogens over and break the old CO bond. Remember, the activation energies are different for the forward and reverse processes. We can also use our models to think about orientation. The way we believe the reaction to occur is for hydroxide to come in on the opposite side. So what if hydroxide collides with the left-hand side of this molecule? Nothing's going to happen. That won't work. What if hydroxide comes in on the right side but comes in hydrogen end first? That's not going to work either. They have to come together with hydroxide on the appropriate side of CH3I and the oxygen end in for the reaction to occur. Concentration and temperature are factors that you, the experimenter, have control over. Activation energy and orientation are factors that you can't control. However, you often can change those in your favor if you use a catalyst. Many biological reactions use enzymes as catalysts. They may hold substrates together to improve orientation, and they can weaken bonds or even change the order in which bonds are broken to lower the activation energy.